So just a reminder, I guess I should announce this since I just referenced it. So reminder, I have the lecture channel open on Discord on my phone, so I watch that. If you have questions you want to ask during lecture, feel free to put them in the Discord. We also have a second channel now, Lecture Off Topic, so if you just want to like make memes and joke around during lecture, just hop in Lecture Off Topic and keep it there. I want to try to keep the lecture channel clean because that should be things like that need my attention so that I can address the questions and stuff like that. Not that a little bit, I'll tolerate a decent amount of off-topic in lecture, especially if it entertains me and makes presenting slides less boring. But if it's way off-topic, make sure it's in off-topic. All right, so let's talk about stacking queues. So I'm talking about stacking queues today, but I'm really doing this as a way to solidify our understanding of linked lists. So this really is another linked list lecture, but as an application of linked lists, we're going to see stacks and queues. We're going to do the same thing next week with trees. I'm going to introduce trees next Monday, and then on Wednesday we're going to talk about binary search trees. And I don't necessarily care how much you understand about binary search trees. I care a little bit. But I really want to know that you can take this idea of a tree and apply it to solve some real world problems, actually do something with the data structure instead of just having the data structure for data structure's sake. So stack and queue is an application of linked lists, and then we're going to use a stack to actually convert infix expressions to postfix expressions. We'll talk about that towards the end of lectures. But all that to say, these are all applications of linked lists. The topic is still linked list. That's what I really want you to understand. That's what I really want you to focus on. So stacks and queues. And we're on our first Enemy AI lecture task. Monday had no lecture tasks, but today this is our lecture task number 1. It's all about linked lists. I won't go through the details of these, but we're going to have a linked list of player locations in our game. And we want a way to be able to identify the location of a particular user by navigating that list and then finding that user. And then finding the closest player to a specific point by going through the list and doing a minimization problem. What's the closest player, and then finding that player. So playing with linked lists, and we will be using the linked list node class, the one that we've seen in lecture. That's the one that you'll have to use in your assignment. So we're not using a Scala list for these ones as the input. All right, but stacks and queues. You don't necessarily don't really need a stack or a queue for that lecture task either. But you have to have an understanding of that linked list node. So stacks and queues, these are two data structures that we're going to build off of linked lists. These data structures have the functionality of a linked list, but with some of the functionality restricted. So these are really like restricted linked lists that just some operations are not allowed. The only operations that are allowed are very efficient operations, and for this context, those operations are actually all O of 1. So we can only have O of 1 operations on these things. The only methods that we're allowed to call are all going to be O of 1. And let's just go into building them. My hot take on this, by the way, since stack and queue are just linked lists with some of the functionality removed, like just use a linked list. Just use a linked list, and then if you actually wanted a stack, just use a linked list as a stack, or use your linked list as a queue. But we do want to focus on, what we focus on in these lectures is not like how we're going to do things in the code, but the idea of a stack and a queue. If for no other reason, just because these are two terms that you're going to hear throughout your computer science, throughout the curriculum, and throughout your career. People are going to be talking about stacks and queues. Hell, we've talked about the memory stack in this class quite extensively. That's just a stack data structure. So this idea of a stack and a queue, if you say it's a stack, people are going to know how you're going to use that list. They're going to understand a lot of things about that. So it's more of the concepts of stack and queue that we're concerned about. You might not even use a stack or a queue in your code anywhere. You'll just use a list and then use it as a stack or as a queue as the certain condition calls for. For what it's worth, Scala does have built-in stack and queue classes called stack and queue, and you can use those if you need a stack or a queue. You're welcome to use those, but again, I'd recommend just using a list. So a stack is going to be a last in, first out data structure. You can think of this as a stack of objects, here a stack of folders, or a stack of anything. where you can only access the element on the very top of the stack. This applied with stack frames. The stacked frame at the top of the stack, which was visually the bottom, we always draw the stacks from the top down for program memory. But in the stack, it's the stack frame that's on the top of the stack is the only one that's active. All other stacks, all other frames on the stack are effectively inactive. They cannot be accessed. You can only access the top element. You can only add stack frames to the top of the stack, and you can only remove the top stack frame. That's a stack data structure. If it has those properties, it's going to be a stack data structure. So in this example, we can't go to the middle folder here and just pull this folder out. You might knock over the stack. I mean, sure, you could very carefully just pull out that folder. But with the stack data structure, we're saying you can only access the top element and only add elements to the top. Stack has two methods. If you have these two methods, you got yourself a stack. Push and pop. Push elements to the top of the stack. Pop elements off the top of the stack. Certain implementations will give you a third method, either peek or top. It's called something different in every language, I feel like. If you just want to access the top element without removing it from the stack. So it's an optional third method. But these two methods, this is all you need to define a stack. And our stack is only going to have these two methods. Push to the top of the stack, remove, pop to remove from the top. And this is what that looks like in code. So we're going to use our linked list node, which defines a linked list, and use that to build our stack and queue. So here I have a class stack, a stack class, which takes a type parameter, so we can have a stack of whatever the hell we want. And it's going to have a state variable that is the linked list. That's what's going to store all of the data, but we're going to hide that information. We're going to hide that information and only allow people to access it through these two methods. Of course, in this case, they could just access top directly, but users shouldn't do that. They're going to interact with that data just through push and pop and embrace the idea of a stack. Push is going to add that element to the top of the list, to the front of the list, and update the pointer, update the reference. And then pop is going to take that value from the top of the list, pop it by removing it by updating the next to the next, like we saw how to remove an element from a linked list. We're going to remove that element, and then we're going to return the element that was popped. So in this way, if we want to access the top element of a stack, we actually have to remove it from the stack to be able to access it with this implementation. That's why some implementations, some languages will have a third method, some peek or top, which just shows you, just returns the top element without removing it from the stack, for what it's worth. We're just going to use these two and return a reference to the object that was popped, which gives us all that functionality. If we want to use a stack, we're going to call push and pop. We're going to create a new stack, push elements to the top of the stack, pop elements off the top of the stack. And this stack, at this point, after we pop this element, is going to be a stack with 3 on the bottom, then 7, then 2, and -5, which was just popped off of the stack. Now we can get that same exact functionality with a list. And one of my favorite comments in the Scala documentation is in the stack class itself. So Scala does have a built-in stack, and they have a comment that says exactly the same thing I say, my exact feelings about stacks and queues and lists in relation to each other. Right in the stack class itself, the devs left a note, the Scala devs left a note that said, you know what? Don't actually use this. What are you doing? Just use a list. Just use a list. Why would you ever use this stack class? It's just a list with less functionality. If you use a list and you want that functionality later, it's sitting there for you. But if you use a stack, you're restricting yourself to just push and pop, which is not the best thing. But the stack is efficient. Both push and pop are O of 1 operations. We're going to see in a little bit why those are O of 1 and why why it's so nice, just using these two methods, memory-wise. But that kind of contradicts what I've said earlier. Lists, because this is true for Scala lists as well, push and pop, or rather prepend. I should explain how we're doing it. So prepend, if we use the prepend operation, and then update our stack by removing the first element this way, this does the same thing we did on the previous slide. That's the same as pop. This is going to give us the same functionality as the previous slide in a very optimal way, but this works with Scala list and the linked list node that we saw. So the Scala list is a little bit tricky there because Scala lists are immutable. Every time you prepend an element to a Scala list, it is a linked list. We're prepending that element, and it's returning a brand new list with that change applied because lists are immutable. It can't just modify that list. It's creating a brand new list. So how is this returning a brand new list with 273 and updating this reference and doing that in O of 1, doing that extremely efficiently? Yeah, LO4 is like a hybrid of everything. We're going to use OOP and FP throughout LO4. We get to use everything now, everything at our power. So I want to focus on this line of code right here. The state of this stack as we're pushing -5 to the stack or prepending -5 to the linked list, depending on what lingo we want to use. We're effectively using a list to simulate a stack. So either way, either way of referencing it says the same thing. So let's take a look at what happens there. So right here, right after this line is executed, this is our exact linked list. And then in the stack variable, we have a reference to this linked list node right here. This linked list node has a reference to the next linked list node, which has a reference to the next linked list node, which has a value of null for its next. When we prepend -5, we're going to create a new linked list node with the value 5 and -5, and its next refers to the first node in the original list. And then stack is updated to a reference to this linked list node. When we do that, our original list with 273 was not modified at all. So we didn't violate the immutability of this list at all in any way. This list in the red box, the list as it was before we prepended -5, is identical to the way it is. It can be immutable, and that's fine. It just stays exactly the same. And then when we prepend -5, we're reusing that entire list by just storing a reference to that old list. So we're reusing all of that information instead of copying an entire new list. So now stack is a reference to this node, which is effectively a reference to the list -5, 2, 7, 3. When we remove the first element, we're going to update the reference of stack to, again, refer to this node here. This new node is still going to exist, but we're just going to update our pointer, or update our reference, and refer to this node again. If we refer to this node, if the stack variable refers to this node, we effectively refer to the list 273. If we popped again and referred to this node, we're going to refer to the list 73. And whenever we do that, we're not changing memory at all. So we're not violating the immutability of a list. Technically, there are 4 lists in memory: the list 3, the list 73, the list 273, and the list -5, 273. There are 4 lists in memory here, depending on which node we refer to, but all of those lists can exist simultaneously, and we can reuse memory. All 4 of those lists reuse this node. It just matters what node we're referencing, what node we have a reference to be able to change the list. So when we push and pop, the original list, the original stack, is not modified. So that's how prepend is very efficient, because we're just creating a new node, and its next refers to the old head of the list. We don't modify anything else in the list, just create a new node, refer to the first element of that list, and we have a list that's one element larger without changing anything else in memory except creating the new node. So it's an O of 1 operation. If this list were 1,000,000 elements long, it would still be the same exact amount of work. Create a new node and have that node refer to the first element of the list. And now you have a list of size 1,000,001 with very little work. Prepend, very, very efficient. Any questions so far? We feeling good about stack? And this is the big part to understand. This is where we're looking at lists. Why prepend? I've talked about this all semester. Prepend is efficient, append is terrible. We'll talk about append next when we talk about queues. But any question, especially on the list, the linked list implementation here? And to answer the question, Chad, a little more, I'd say right now we're embracing a lot more OOP than FP. I'd say it's pretty much an OOP paradigm we're using right now. And on Monday it was more FP. We had more first order functions floating around. But it will be a hybrid. All of LO4, we're going to use functions and objects throughout. We're going to have state, and we're going to have control flow. We're going to have everything. Yep, exactly. Demios. Yep. Exactly what we're doing. So we didn't modify the original list at all when we prepend. We're not modifying the original list at all, but we're still returning a new list with that change applied, with the new element added to it, because we're just, instead of referring to this node, we're now referring to this node. And that effectively adds -5, prepends -5 to the list. Just by playing with references. We talk about references all the time because they're important, they're powerful, they're useful. And it's how computers work. We use references in a lot of things. Just update the reference, we very efficiently prepend to the stack. Or prepend to the list, push to the stack. Prepending and reversing or appending? I would guess, it depends on the implementations. They both be pretty bad, but I'd say appending would be faster. It would be my guess. But yeah, Nicholas is right. They're asymptotically equivalent. They'd both be O of n with immutable lists. Now, the linked list node class that we wrote, that we saw on Monday, that's a mutable list, and then both append and prepend are both O of 1 operations. But if you have an immutable list, so Scala's list, since it's immutable, append is much, much slower, is O of n. But my guess is that the specific implementations would append quicker than prepend and reverse. Actually, I have one more thing to say about that. If, like we saw earlier, I forget even how far back it was, but I had a lecture example. It was when we were doing sorting, where I needed to append. I had the need to append, but instead I prepended, and then after I was done prepending all of the elements, then I reversed. That got us more efficiency, because I wasn't reversing after every single prepend. So if you can prepend all of your elements and then reverse, that's way faster than appending each time. And depending on the application, you can get asymptotically faster that way. I got asymptotically faster by doing that in the sorting examples. But if you're reversing after every single prepend, then they're asymptotically equivalent. All right, so Depends on how heavy the pancakes are. Yeah, I forgot to mention that part too. Sometimes I forget things. So let's talk about queue. This is going to be our first in, first out data structure. Just as the name implies, it's just like queuing up to a line. Like you're going to pistachios and you wait in line. You're going to append yourself to the end of the, we can think of it as a linked list, but to the end of the line, and only the person at the front of the line is getting served. So we append to the back and remove from the front. And that's our queue, that's our first in, first out data structure. First, we have two elements, two methods, just like before, except they have a little bit different functionality. In queue is going to add to the end of the line. That's somebody joining the line, joining the queue. And DQ, remove the front element, the first element from the queue. The code is a little bit extra. There are a few extra checks that we have to do, and we have to have references to the front and back element. We have to work at both ends of the linked list. So we have to have two references to the front and back. And I have some kind of gross looking null checks to be able to figure out if the list is empty. Like for example, if you DQ the last element, then the front and back should both be equal to null. So I have to have a conditional there. All right, a little bit extra checks, but same idea. We're going to prepend to the front of the list, and we're going to remove from the back of the list. Oops, I did say that backwards, didn't I? I was even looking at it close to make sure. I'm going to append to the back of the list and then remove from the front of the list to be able to get the functionality that I want. Oh, and something I forgot to mention, I do want to make sure I say this, or else I'll feel bad. This will break if you pop from an empty stack. This will give us a null pointer exception. So if you're looking in my code and being like, that's going to break, yes, it will. It will break if you pop from an empty stack. This is actually common. I mean, usually you would throw an error here, but this is actually common for implementations of stack. If you pop from an empty stack, your program will crash, you'll get an error, you'll get an exception. So my code will do the same thing. You pop here, pop from an empty stack, null pointer exception. If you DQ from an empty queue, you're going to get a null pointer exception. So these data structures will crash if you use them, I don't want to say improperly, but if you try to use them in a way that they're not built for. DQing, what does it mean to take the next person in line when the line's empty? I mean, hopefully the restaurant doesn't crash, but you're not going to get functionality out of that. But that's common. If you take like Scala's stack and just pop from the empty stack, your program will crash. All right, sample usage, same idea as the stack, except this queue is going to be in reverse order of the stack. This queue will be 3, 7, 2, -5 instead of the reverse order of insertion as it was for a stack. So this queue is going to have 3 at the front, then 7, 2, -5. And when we DQ, we're going to DQ the value 3. Scala is built in, so we're building a mutable list, linked list with linked list node. Fun fact, Scala's built-in queue, also built on a mutable linked list. They don't even bother trying to write an immutable queue because there's just no good, there's really no way to do it efficiently. And that's because appending is slow. So let's finally address this. I've been saying this all semester as well. Every time you append to a list, when I did it in the sorting lectures and everything, appending to the list, slow. It's very slow. Appending to an immutable linked list, very slow. So let's finally see why. Let's visualize this thing. So let's talk about when we queue up 3. It's not the order I did this in. Damn it, Jesse. I have that backwards. That should be -5 at the end and 3 at the front. But when we enqueue 3, when I have the original list in the red box again, this is the list before we enqueue 3, where 7 is going to refer to null. Its next is going to be null. When we append 3 to the end of this linked list, we have to update, we'll create the new node, we'll have that node refer to null because it's the new end of the list, and then we'll update next of this node here to refer to the new node that we just created. When we update that next, we have changed the list that's in the red box. We've changed that original list. We have to change this list, this value right here, to append that element there. Since we have to make that change, this list can't be immutable. We can't do this with an immutable list because that list had to change. We had to change it. We have to remove that null and replace it with a reference to the node that we created. Since that list has to change, it can't be immutable, so this can't be an efficient operation. When you append to a Scala list, it's got to create a whole new copy of the list with your change applied, an actual full copy of the entire list. It's an O of n operation. If you have a list of size a million elements, and you append something to the end of it, you now have a list with 1,000,000 elements and a list with 1,000,001 elements, both in memory. And you probably have a list with 999,999 elements, 9 and 8, so on. You probably have 1,000,001 lists in memory sitting there, all copies of all of the data. Some of you, depending on how you write the code, you can run into this in homework 1, as early as homework 1. If you're iterating through the list of cities and you're appending to a list for every single city you read and building a big list, a data structure with all of the city data, which you don't need to do for homework 1. You shouldn't be storing all that data in any data structure. But if you do, there's nothing wrong with it if you do either. But if you do, and you're appending to the end instead of prepending, you'll notice that your program runs slow as crap. It takes forever to run that program. If you didn't do that, it might be worth going back to homework 1 and making that change. Just write code that does that, reads the file and appends, and change it to read the file and prepend, and just feel the difference. It's extremely different in terms of efficiency because of this right here. Because you're using an immutable list, but appending to the end, the list has to change every time, so a new list has to be created. All your data has to be copied every time you append. Very, very slow operation. So whenever you can, avoid appending when you're using a Scala immutable list. Avoid appending whenever you can prepend instead. And that's the big thing that I want to focus on in this lecture. That's probably the biggest takeaway. Why prepend is efficient and why append is not. And it all comes down to updating this reference right here. Just because that reference has to be updated, the list can't be immutable, copies have to be made, things get inefficient real fast. By the way, just since I kind of mentioned it, I don't think I've mentioned it yet this semester. Whenever you're feeling like really overwhelmed and feeling like you're getting crushed by the current assignment, I always recommend going back to an old assignment. This might be a nice time to go back and visit homework 1 again. Go look at Pale Blue Dot and look at something about that assignment that really gave you trouble, that you really struggled with understanding, and go back and like rewrite it or just revisit it in some way and look at it again. It's helpful to know, like especially a course like this that can kind of crush your soul, is going back to something like that and realizing how far you've come. That challenge that you had back in homework 1 should feel really easy now. That difference, like that's how much you're growing, that's how much you're learning in this class, that's how much better you're getting as a developer. You're constantly getting better every day. And it's hard to see that when you're in the thick of it, but if you jump back to a homework or jump all the way back to a 115 assignment that gave you a lot of trouble, go back to one of them, go back to UB Infinite and do some UB Infinite questions and just feel and visualize how far you've come. It can really be a nice confidence booster to remind you that, because the way our courses are designed, we're trying to always keep you in a state where you're being challenged, on purpose. We're always pushing you forward. So if you go back a little bit and see how much you've grown, it can really help you realize like that you're doing great, that you're surviving 116, you're doing awesome. It can be hard to feel like that when you're in the thick of it, but you're growing a lot, you're learning a lot. And it's tough to learn a lot. You should feel the struggle a little bit at least, because it's just a lot of hard stuff that you're doing. But if you go back to one of those old assignments, it can make it abundantly clear like how far you have come. Making material. Goodness. All right. So let's see an example. Let's use a stack. Oh yeah, or go. Yeah, do what Cole said. Go back to PVD and don't use any conditionals or variables. Well, you can't get rid of both of them, but try it without conditionals and try it without variables. Then you might go back to crying, though, for bad reasons. Without variables, I don't think that would be too tough. Just embrace some functional programming. It would be at least as hard as LT4 on the current assignment on genetic algorithm, where you got to read a file and get all the data into a data structure without using any variables. You would have to do something similar to that to read the cities files. So it would be at least as hard as LT4 in the current assignment. But not too much harder, I don't think. I don't think there's anything that would really trip you up on that. All right, so after finishing genetic algorithm, then go back and do homework 1 without variables. I think you'd be able to handle that without too much difficulty. So let's talk about expressions. I'm going to use this again as an example of using a stack, where we could use a stack in practice. So before that, I need a little bit of background. Infix expressions, this is the way you're used to seeing math. We put operators between operands. So if we want to subtract 12 and 4, we put the subtraction operator, right in between the two operands. Shouldn't need much more explanation than that. And then we have order of operations. And then if we want to override our order of operations, we slap in some parentheses. To evaluate an infix expression, we're going to use PEMDAS to remember our order of operations. And then just go through everything and evaluate according to that order of operations. So start with inside the parentheses, left to right. Evaluate this first. When we get here, division and multiplication come before addition. So we're going to compute the division first, then the multiplication, then the addition last, and then the subtraction and get our -6. Better not be any news to anybody in this room, but just a refresher on how that works. What's up, Cole? Now let's put a spin on this and talk about postfix expressions. Postfix expressions, instead of having the operand between the two operators, we have the operand after the two operators, where the namesake post comes from. We have the operator after the two operands. With this is the same exact expression that we saw in the previous slide, except we have quite a few advantages with this. No parentheses, no order of operations, very easy to write a method that computes these. If I said, for one of the homeworks, I said, write a method that takes a postfix expression and evaluates it, it's not too hard to write that. The algorithm is scan until you find an operator, take the two previous values, those are going to be operands, and evaluate that. Very simple to write the program. There's a little bit of tricks in there, but nothing too difficult to train a computer to evaluate a postfix expression. That's one big reason why we like postfix expressions. Computers can evaluate them very simply, very easily. The disadvantage is it's hard for us to read unless for some reason you've been trained on postfix expressions for whatever reason. So easy for a computer, but hard for a human. And if you don't believe me that it's easy to write the computer program to evaluate this, I do mean that relatively. So compare that to if I gave you an assignment that said, write a method that will evaluate infix expressions. Okay, now you got to code order of operations, you got to code parentheses, you got to scan the entire expression to figure out what you're going to evaluate first. There's quite a bit extra going on to evaluating those. But postfix, much easier by comparison. Much easier to write the algorithm that's going to evaluate this as opposed to an algorithm that's going to evaluate infix expressions. In fact, even if we add like exponentiation here, we won't have to change our code at all. We just have to add the idea of exponentiation to it. But we don't have to add that to like our order of operations table or anything. We don't have to modify anything. We just say, here's another operator that you can use. Very nice to work with. When we want to evaluate this, we scan for an operator. The previous two values are operands, and evaluate it. 12 minus 4, 8. And then just replace that in, like right where it was, in place. Scan for the next operator, division. 9 divided by 3 is 3. Scan for another operator. 3 times 2 is 6. We hit a plus. 8 plus 6, 14. Subtraction, 8 minus 14, negative 6. We have the same value. It's the same expression that we saw in Infix notation. It's just postfix notation. So we have a few properties of these. We have nice pros and cons of these two. We would like to use infix notation as human beings because we can read that, if for no other reason, just because we've been trained with infix notation. It's just what we happen to use, what happened to be taught in grade school and every school. Grades, if one grade school said we're going to teach postfix, that's quite a disservice to the students, I guess. I don't know where I'm going with that one. But anyway, we all know this. We know how to do this. But we would like to convert those into this to be able to be represented in the computers. We have efficient algorithms, easy algorithms to write, O of n algorithms, in fact, where this we might have to scan through a few times, go back and forth. I don't know off the top of my head, actually, if we have an O of n algorithm to do that. I would assume not. I'm kind of wondering. But anyway, it's a lot easier to work with. So what we'll see is this shunting yard algorithm, which is going to convert infix to postfix. We're going to convert this infix expression to this postfix expression. They're both the same expression, but we're going to convert the notation. To do that, we're going to read the expression from left to right, copy any operand over to the output, copy, which I forgot to put on the slide, but copy open parentheses to a stack, or push them to a stack. Whenever we see an operator, or whenever we see a closed paren, we're going to take whatever's on the stack and copy it to the output until we see an open paren. And whenever we read an operator, we're going to pop from the stack and copy the stack to the output until the top of the stack is an operator with a lower precedence. Do I say lower or higher? Lower precedence, meaning an operator that should be evaluated after the one we're currently considering. And at that point, we're going to push the one we're considering onto the stack. Or if the stack's empty, or if open paren is on the top of the stack. So that's our whole algorithm. Don't worry, we're going to go through this step by step and see how this algorithm is applied. And when we get to the end of the input, just copy everything else that's on the stack to the output. So let's take a look at this and just see how we get to use a stack. Again, this is an example of where we could use a stack, where a stack comes in really handy. And again, I would probably use an actual list for this, but I would use it as a stack because all I'm doing is pushing and popping, or prepending and removing the first element. So we start with an open paren, push it to the stack. Operand just gets copied to the output directly. Operator, we're going to go through our logic. We're going to look at the stack, the top of the stack, and as long as the top of the stack is we're going to pop from the stack until the top of the stack is an operator with lower precedence, or the stack is empty, or the top of the stack is a open paren. We have an open paren here, so we're going to just push operand, copy to the output, and now we read our first open paren. We're going to copy the stack over to the output until we see the open paren, the matching open paren. So copy that subtraction out, the parens cancel each other out, and we have our first part of the output, our first thing, 12 minus 4. We have an empty stack, so push the operator, push the open paren, copy the operand. This, we have open paren, same situation we had last time, so push that to the stack. Operand, copy it over, and now we have our first decision. We have a division, and we're going to look at the top of the stack, and we're going to say, we're going to compare the order of operations and say, is the top of the stack something with lower precedence? In this case, it is. Addition should be evaluated after division. So the top of the stack is already an operator with lower precedence, so we're going to push division onto the stack. Operand, just copy over. Now we have another decision. Multiplication, we're going to pop from the top of the stack until the top of the stack has an operator with lower precedence. These are tied in precedence, so we're going to pop the stack and get that division over here. Now this is lower precedence than multiplication, so we push multiplication onto the stack. 2, copy it over. We hit a close paren, and the rest is just cleaning up the stack. We hit a close paren, so pop off the stack and copy it to the output until we see the open paren. And now we've reached the end of the input, so everything that's on the stack, get it over in the output. And we've converted that infix expression to a postfix expression. So notice when we got here, like this, we know by looking at the infix notation that we should compute division, then the multiplication, then the addition. And you notice that that's the order in which they were copied to the output by making these decisions. Addition went on the stack, division went on the stack. When we got to multiplication, we said, oh, we got to a point where division has to be computed before this multiplication. So get that division over in the output. And when we hit the close paren, we get the multiplication and the addition. We get division, multiplication, addition in the right order when we're using this algorithm. And the algorithm design takes care of all those order of operation decisions. It's definitely O of n to compute infix, by the way, thinking about it for a second. Because you just run shunting yard and then compute the postfix, and shunting yard is O of n. I can read, I've read before. All right, any questions? All code is just hacking, by the way. All code is just a made-up mess of garbage. I shouldn't say it like that, but I know it's a joke in chat, but I'll get a little bit serious about it. Like, programming hasn't been around that long. Like, in the grand scheme of things, like maybe 50 years. Depends where you count, like the start. Like, is it where it technically started or where it became popular? But not that long. Nobody in this industry knows what the hell they're doing yet. Like, we haven't figured anything out. Everything's just like a guess, basically. Including teaching. If you notice that our computer science courses, like if you compare this course to like Calc 2, a lot of you are taking both of them, your Calc 2 course is going to be a lot more defined because calculus has been around since, I don't know off the top of my head, 1400s, I think. They've had a lot of time to figure out how to teach calculus. We haven't had a lot of time to figure this stuff out, like in the grand scheme. Like 50 years, it sounds like a long time, but even then, like 20 years ago, the landscape was completely different in computer science. So yeah, we're all just kind of hacking things together and trying to figure out what works. In like 200 years, maybe we'll have things figured out a bit in this industry, a bit more. Maybe it'll look more like engineering, where there are like sub-disciplines and stuff, and things are a bit more defined and a bit more clear. But yeah, everything's just kind of a mess. Like every time we get some structure anywhere in this industry, technology moves forward and we got to rebuild. And I guess so. Oh yeah. Let me end that on a positive note. You have a lot of opportunity to shape this industry because of that. Like you can get out there and really like make a huge difference. If you have good answers and good ideas and go into their company or make your own startup, there's huge opportunities for you to make a really big impact. So I don't know, go out there and make a big impact. Do some cool stuff. That's the note I'll end on. Take care, everybody. I'll see you all on Friday.